Now, the purpose of creating the samples is so that we can estimate values or infer something about the population. These inferences are going to be point estimators. Point estimators are statistics that estimate a parameter of a population, regardless of what it is we're looking for. The three parameters of a population are denoted by Greek letters: mu, which is a population mean; sigma, which is the population standard deviation; and a letter p, which is the population proportion, or percentage of a population that does one thing or another. For every sample, an inference is made about the population. For example, an average in a sample could be a very good estimate of the population, especially if the sample is large enough. So think about, in a university, you grab a sample of folks who have a certain GMAT score or SAT score. You take that average, and you can infer that that would be a good estimate of the entire population at that university, assuming that your sample was big enough. If you only did a sample of 4, that might not be a very good sample. But if you did a sample of 50 or 100, it might actually be very close to the actual average of the entire university population's SAT score. Similarly, a sample standard deviation is a good point estimate of the population standard deviation. And a proportion from a sample, such as a percentage of graduate students in a sample, would also be a good estimate for a proportion in a population. For example, in the case you ask 100 students whether they like the food at the given cafeteria, and the answer is, let's say, 55%. That is probably going to be a very good estimator of everybody in that university who has an opinion about that cafeteria. For the most part, we're going to deal with the mean as a point estimator, and we're going to deal with the proportion as an estimator. We won't really do anything with the standard deviation. But the point estimates of the sample relate to the population parameters and are denoted as following. The x bar, so that bar over x, is the sample mean, and that refers or infers about the population mean denoted by the Greek letter mu. Similarly, a point estimate S is a sample standard deviation, and it is a good inference for the population standard deviation of sigma. Similarly, a sample proportion, which you might see in some books as p with a bar over it or p hat, that's a sample proportion. And then you're going to see this italicized p, which is the population proportion. So using a previous data set that we had seen before, the sample data set for Old Faithful, the population parameters can be inferred about the duration of the eruption. So a subset of the entire data, 222 observations, is provided here on the right. So we've just taken a few of them. They range from 4.4 all the way down to 2.0. They're cut off again with those 3 dots so that I can fit it here on the screen. But what we'll do is we'll take the average of a sample, 222 observations, and that average is 3.6, again denoted by x bar. 3.6 is a point estimate of the population mean, meaning that the eruption is around 3.6 minutes. Point estimate for the standard deviation is denoted by the sample standard deviation again here, and that's going to be 1.084. So 1.084 is a point estimate of the population standard deviation. What would happen if from a large data set, 100 samples were drawn? So we take one sample of a set of data, and then we take another sample, another set of data, and so forth and so forth and so forth. And we take all of these samples together, and we take all the means from them. Okay? These 100 data points, these 100 means for each one of those samples that we've chosen can be combined into a new data set. So consider the obtained means from the data set below of dog body temperature. So this is a whole new data set. In one sample, it was 100.93. In another sample, it was 100.97, and so forth and so forth and so forth. The means of these samples will form their own distribution called a sampling distribution, and it is the distribution of the means. Here are a few sample histograms from those samples. So the red line is the population mean of 101.3. The blue line is plus or minus 1 standard deviation, and the green line is plus or minus 2 standard deviations. So you can see here that for the most part, each one of these samples seem to fall within that 101.3, But they're not all the same. They shift a little bit to the left, they shift a little bit to the right. But in general, that red bar seems to fall within that big mean there, within the big bar of the histogram. As shown in the previous graphs, the means of each of the samples tend to be near the population sample. In fact, running 500 independent samples, the mean of the samples, so taking the average of all of the averages, was 100.30. It's extremely close to the population mean. Further, those means that we got will follow a normal distribution. Therefore, the expected value of all of the sample means is going to be equivalent to the population mean. So if you took a whole bunch of samples, took their averages, those averages would then form a normal distribution. And the expected value of that normal distribution would be equivalent to the population mean. Using the previous example, the standard deviations of the sampling distribution is proportional to the population standard deviation. So as the sample size increases, the standard deviation is smaller. So this notation here, sigma x bar, is the standard deviation of the sampling distribution. And it's a little bit different because it says it's equal to sigma over the square root of n. As the sample sizes increase, the standard deviation gets smaller, meaning that the variance narrows. Now you think about this, is that as we get more and more data, the standard deviation or the variance that's spread around the mean gets smaller and smaller and smaller, so that we're getting very, very close to that mean. There is no spread. It will be exactly the same way. The formula for the sample distribution is specifically for an infinite or unlimited population. However, sometimes a smaller population is desired to be estimated. So if a company has 10,000 employees but not all can be surveyed, a sample can still be obtained and analyzed to obtain point estimates and sampling distributions of the company. Consider that all 10,000 employees were able to be surveyed. If that were the case, then the standard deviation of the sample means would have no error, and thus would be close to zero. With n sufficiently large, the denominator would be significantly high, making this fraction close to zero, meaning your standard deviation is zero. And if you think about it, if the standard deviation is zero, meaning there is no spread, the only thing you have is the mean itself. When the data is sampled from a finite population, then an adjustment has to be made. If the sample is greater than 5% of the population, this adjustment is required to correct for the fact that the sample standard deviation is affected by the larger proportion of the data. What this means is that if you have a large sample in which it's greater than 5% of the data, you're going to want to correct a little bit, call this finite population correction factor, because your sample is so large that that the sample is going to be affected by this larger proportion of data. And so you're going to end up with a slight issue if you don't make this correction. So it corrects for the proportion of the population standard deviation to the square root of the sample size. This c that we have here is the square root of capital N, which is the total number of observations we have, minus little n, which is the sample size, divided by capital N minus 1. So if you think about it, what will happen is that as you end up with a very large sample, you're going to end up with that numerator getting closer and closer to zero. So let's take a look at an example. Assume that the capital N is 10,000 and lower n is 5,000. We would end up with the square root of 10,000 minus 5,000 over 10,000 minus 1. That's the square root of 5,000 divided by 9999. That's equal to 0.7071. Therefore, the sample distribution's standard deviation is 0.707 times the population standard deviation, divided by the square root of n. So we just replace this c here with the 0.7071. So it's a weighted factor of about 70% of what the other one is. Let's examine a few other scenarios. One in which the sample size n is very close to the bigger n, and another where the n is very small. We've done it a few times here. So assume n is 10,000. The following cases are going to show what c is computed as. So when little n is 30, that means it's only 0.3%. So with n very small, c is close to 1, so the correction factor has no real impact. It's 0.9984, that's almost exactly 1. And that's why we say if it's not 5%, we don't worry about it. In the case where little n is almost the whole data set, we would end up with, say, the square root of 1 over 9999, which is the square root of 0.0001, which is equal to 0.01. So with a very large n, c becomes very small, and thus the full equation, c's standard deviation divided by the square root of n, approaches 0, meaning there's no standard deviation to work with. In the case of where little n is 1,000, that's 10% of the total, we would have a correction factor of 0.9486, and it does have an impact. And in the case of 5%, which is our limit, we have 0.975 as our number, and so it is small and should have little impact, but once you start getting above that number, it will start having an impact. But the default is at 5%. If the sample is greater than 5%, then we start using that. If the distribution of the population is known to be normally distributed, then the distribution of the sample mean distribution will also be normally distributed, regardless of the sample size. Even if the distribution is not known, with a sufficiently large sample of sample distributions, the distribution of the sample mean distribution is also normal. So this basically means if you know that the population is normally distributed, then the sample mean distribution is normally distributed. If you don't know what the distribution is, but you have a large number of samples, well, that's also going to be normally distributed. And the reason behind this is due to that central limit theorem. When the sample distribution is made up of a sample greater than 30, the central limit theorem holds and provides evidence of a normal distribution. Therefore, samples greater than 30 can be assumed to follow a normal distribution. So let's take a look at that standard deviation formula as sample error. Let's take a look at the standard deviation of that sampling distribution. So we said that it's sigma x bar, which is equal to sigma over the square root of n. We will now refer to this as the sample error. It is the approximation of the amount of error or variance from the expected value of the mean. Previously, it was shown that if the entire population was used to obtain a sample mean, the sample mean would be equivalent to the population mean, and there would be no error. Consider the case where n is very large, and take the square root of n, it's also large, and thus the denominator becomes more dominant, making the fraction increasingly smaller. Thus, this fraction ends up being close to 0, when it approaches 0, which we call asymptotic. Asymptotic basically means something that approaches a value, in this case 0, and in this case it's indicative of no error or very little error.